have a look at tonight, week 2, is complex power flow, power factor correction. Remember we talked last week about poor power factor and the supply authorities penalising you because the power factor, the cos phi, is low power factor. So this week more formally at the correction of that. And then for those of you that have got to do the assignment, 4 of you, we'll then move on. So we'll have a go at those calculations, have a go at the tutorial question sheet for a little while this week, and then we'll wrap that up. And I'm going to go through the principles of a 3-phase motor, induction motor, and why I'm doing that will be clearer when we had a look at the assignment. All right. So, from the conservation of energy, it should be clear that the real power supplied by the source is equal to the sum of the real powers of the load or loads. So if there's multiple loads, the overall real power, there's all the real powers added together. The balance between reactive powers must be maintained. This means that the total complex power delivered to the loads in parallel is the sum of the complex powers delivered to each, such that for the following circuit, so we calculate S by multiplying V by I, okay, and the overall current here is these 3 currents added together, so we can rewrite that as V times the bracket of the sum of all the currents, okay, and then if we take those brackets away, i.e. multiply them out, it shows that overall S is equal to the S due to I1 and Z1, the S due to I2, Z2, and the S due to the third load. So we can get to the overall apparent power by adding all the apparent powers together. Yep, just the same as if you've got basic resistive loads, all active power, 3 lots of 10 watts, overall power, that's 30 watts. So we can do all of that with the complex ones as well. We just have to be a bit careful about them being in phase with each other before we add them together, or doing complex arithmetic. Okay? Yeah. So, having a look at an example. The above circuit, the values are as follows. V is 1200 angle 0. Z1, 60 plus 0J. So that's a resistive load. We're going into complex numbers here. We're in the rectangular form. Alright, so that represents just a resistance. Is 60 ohms on the left to right scale, and nothing up or down, no J term. Yeah. And then Z2 is 6 ohms plus 12J, so that's made out of up of 6 ohms that way and plus 12J up that way. And the result is a laser in here with an angle. Alright. And then lastly, Z3, which is a capacitive, has got 12J downwards and 6 ohms this way, and a Z phaser in there. Yep. So this one is Z2 is 6 plus 12J. Z3 is 30 minus 30K, sorry. 30 minus 30J. Find the power absorbed by each load and the total complex power. Yep. So from what we spoke about on the last slide, we know that we could say that ST, the total apparent power, okay, it's called, in this case, the complex power because it has a P part to it and it has a Q part to it, and it's complex. There's S, so it has length or magnitude and an angle from 0. Yeah. We know that ST is equal to S for the load 1 plus S for the load 2 plus S for the load 3. Okay, I am now. All right. So because we can say it's all the apparent powers added together, we calculate the apparent power for each load by multiplying the applied voltage, which is the same for every load because they're in parallel, by the current taken by each load. Yeah. So, firstly, how can we find then I1? What's the way into the information that we've got finding I1? Nearly. It is the voltage. I've got a problem with R in this case because that's Z for impedance. Yeah, I know it's only a resistor, but here we're working with AC and we should be consistent, try and use Z. If we're just talking about the component of a resistance, then yeah, you put R. But overall, that's an impedance. So that's E over Z1. Got a voltage of 1200 and the angle is 0. Yeah, it's the in-phase component. And the impedance for resistor, it's 60 plus 0J, so that's also angle 0 degrees. Yeah. So that's only Ohm's law, that's all it is, except for we've got complex arithmetic. And so we do the 1200 divided by 60, 20 amps, angle, this angle minus that angle is still 0. So our first current is 20 amps, angle 0 degrees. So now what we can do is find S1, therefore S1 I 1 times E, that is 1200 angle 0, the voltage, times, I like to put these in, the degree symbol is important by the way, if you leave it off, radians is assumed, multiplied by 20 angle 0. So the multiplication is multiply the magnitude, so 20 times 1200. And the units of S are volt amperes, yeah, VA, angle 0 degrees. And we can put, with something that big, we'd probably go 24 kVA, angle 0 degrees. Yeah. So that's the first one. All right. And actually, S for that load is actually all P, isn't it? Because that's 0 degrees. So if we were to draw a phasor for this, it would be on the line there, 24 kVA, with the angle being 0, and therefore it's actually P. It's also P in watts. There is no Q. Yep. Next bit, find I2. I2 by Ohm's law is E over Z2 1200 angle 0 degrees. Now we've got a little bit of a problem because our impedance is in this form of 6 plus 12J. So we got one number in polar form and one number in rectangular form. Yeah, so plus 12J converted to polar equals, convert on the calculator. Ohms, angle, you're in radians. 63, 63.4 degrees. Yeah, okay, guys, lads and ladies, so that conversion gives this impedance as 13.4 ohms, angle 63.4 degrees. So I2 is equal to 1200 angle 0 degrees over 13.4 angle 63.4. And what I'd suggest is, most times in these calcs, when I calculate an answer, I'd probably do the conversion with it as well and just write it down, because 9 times out of 10 you're going to want it later in the other form. Okay? And that comes out to 89.6 amps. Does that work with civil? It's an inductive load, that particular one, isn't it? Z2. So, and current is lagging, so it does work. Yep. So we've got I1 and I2. Now we need to find I3. It's going to equal, well, first of all, oh yeah, we haven't done that, have we? Jumping the gun, aren't I, Lewis? S2 is equal to E times I2, which is 1200 angle 0 times 89.6 amps angle minus 63.4. And that equals 33,930 angle 45 equals 33.34 kVA. Only gone up from 64 VA in 33,000. I don't think we'll worry about that for you. kVA angle 45. To the nearest kVA. Right. Now we've got 24 kVA angle 0 for S1, 108 kVA angle minus 63.4 for S2, and 34 kVA angle 45 for S3. We need to add them all together. So S1 was 24 kVA angle 0, S2 was 108 kVA angle minus 63.4, and S3 34 kVA angle 45 degrees. How are we going to add all them together? It's the easiest way. What do we need to do to use a calculator? Put them all into rectangular form, yeah. Unless you know some fancy geometry and want to use the sine and cosine rules and take all day about it, convert them to rectangular. Then we can add them up easy and convert back. This one's easy because that's 0 angle, so that's going to be 24 plus 0J kVA. .4 I got here, minus 96.6J kVA of the units, and the last one 24.0 plus 24.0J kVA. Yep. Now, what we do is add them up column-wise. So we add up the real part, add up the imaginary part separately. What do we got? 96.4. 72.6J kVA. Yeah. Now convert that to polar, and ultimately you're going to want your final answer in polar because that tells you how many VA it is in terms of magnitude. What is it? No, well, be careful with yeah, yes, yeah. As the um, you're better off going by. Trying to think here. No, that's all overall inductive. You're drawing a much bigger inductive load than you are capacitive. You've got to watch that angle because that switches when you need to be in the either the current or the impedance one to know about the lead and the lagging. Yeah. We're not talking about current here. We're talking about power, reactive power, active power, and apparent power. Yeah. Because what's interesting about these two different methods of showing this, right, is within that line there, I've got every bit of information about that load that I want. Because this bit, 121 kVA is the magnitude of S, the apparent power. And that gives you the angle of S, because that's a complex quantity. Yeah. But in the rectangular form, 96.4 is the real power in watts. Yeah. And the 72.6 of the J term is the reactive power Q in this case kVars. And that should be P in kilowatts in this case. Yeah. So when you've got S, the two different forms of S, rectangular, is a complex power made up of a power part P, the horizontal component, the reactive part Q, the vertical component, which can be negative or positive, and then the polar version gives you the actual magnitude of S, the apparent power, and its angle from zero. Yeah. Yes. Yes. So you draw it like this. Here's P. Was P 96.4. Kilowatts. Yeah. You'll draw Q as minus 72.6. kVar. And then when you complete the parallelogram, Z goes in there, S goes in there, and that's 121 kVA and that angle in there is minus 37 degrees. Yep. All right. And up here as well, remember, in these separate rectangular forms, you've got the power in kilowatts, 24 for the load 1. Load 2 is 48.4 kilowatts, 96.6 var, kvar, sorry, and the third load is 24 kilowatts and 24 kVars. Yep. All right. All happy with that? Yeah. That's the one we just done. Now I'll put that on that other page. Right. Power factor correction. Last week, we discussed how low power factor results in the power line having to pass more current for a given real watts load. And we discussed how that leads to the supply authority penalising consumers for poor power factor by charging you on your maximum demand. So consumers can improve power factor presented by a high level of inductive load by introducing power factor correction. That involves introducing a level of capacitance into the circuit which is said to provide reactive power to the source, go in some way towards counteracting the reactive power drawn by the inductive load. So because they work against each other, work in opposite way to each other, the reactive power can be counteracted by adding a proportion of capacitive load. Okay. They never go all the way for reasons of you don't really want to get to unity power factor because that causes other issues around resonance. Also, lower diminishing returns in the cost to add the extra capacitance would be not financially viable. Yeah. And if you have a reactive load that changes a lot, then you'd probably have a system of automatic power factor correction, whereas assessing the power factor and switching capacitance in and out to counteract that varying load. Certainly what they had at my last industrial place, with automatic power factor correction. About the length of these tables, probably, set a bank of capacitors, switching in and out. Just sit there and do it all day long and never had any problem with it. Alright, so reactive loads and power factor. If we look at the triangle on the left and consider that as a reactive load with low power factor, it's got quite a steep angle, and the Q due to the inductive load or the VARs is quite high. What we're doing on the right hand side, in red, it adds some capacitance. So we've got some QC down there, not as much QC as we've got QL. We don't try and match it. Because it's working in the opposite direction, the overall Q, I'll call it Q new, is reduced as equal to QL minus QC. We'd still have a lagging current in this circuit overall, because the inductive part is bigger than the capacitive part. but we go some way towards bringing the two back together. Alright, so the overall reactive power Q is reduced, which reduces the phase angle because P, the length of the line P is still the same, but the length of the line S is reduced and the angle is reduced. So it increases the power factor, reduces the apparent power S, and hence reduces the current required to deliver the same amount of active power P. So if this P was 12 kilowatts, still 12 kilowatts. But we could be drawing significantly less current to achieve that because the voltage has stayed the same. The S line has got shorter, so something must have reduced. It must be the current. Everyone with that? Yeah? Example, power factor correction. So, for the circuit above, find the total real reactive and apparent power, the power factor prior to correction, the total current flowing from the source, the value of capacitance required to reduce the power factor to 0.8 lagging, the new total current when the correction is in place. Alright, so we'll go through that together. How we do that. So, first of all, we've got to find the total real power, reactive and apparent power. So, we're going to find the currents separately. So I1 from Ohm's law, E over the resistance, for a single resistance, that is 200 volts divided by 100 ohms equals 2 amps, and the angle is 0 degrees. Yeah. Op 2. That depends what you label it as, Lewis, really, but we'll call it Z1, Z2 then, right? Change it to Z1. How about that? Happy? Happy now? Yeah. Used R and I said no. Yeah. Just making sure you're awake, Lewis, right? Z1 is a resistor. It's just a resistor, isn't it? Yeah? Alright. E over Z2, 200. And now we want Z2 in, we got it in rectangular form, we want it in polar form. So we got 10 I got 22.4 angle 63.4. Equals 8.93 amps. Angle minus 63.4 degrees. Yeah. And now we can find S1. That's E times I1. So that's 200. Angle 0 times 8.93. Oh no, hang on. Two angle 0, isn't it? 400 VA. So actually, that's 400 watts. Yep. Because there's the angle 0. Yep. And then S2. E times I2. 200 angle 0 times 8.93 angle minus 63.4. $1,786 VA angle converting to rectangular. No, that's not right. What? Well, oh, hang on. Yeah, so I got 800 minus 1.5. Yep. So if we add on 400 plus 0J, that's the S1, we get ST. So add them two together, 1200 minus 1596 J VA. Total real power, 1200 watts. Yeah. $1,596 var. Total it's inductive. that equals 1200 minus 1596 J VA converting to polar equals no. .1997 VA, angle 53 degrees. Apparent power, yes, that's 1997 VA, and that's at an angle of 53 degrees. Well, it will be. So we've got, look at this triangle now. 1200, 1596, 1997. Yeah. And we want power factor, cosine of that angle. Yeah. So B cosine is 1200 over 1997 0.6 there or thereabouts. Yep. Okay. I mean, yes, if you want to be absolutely true to everything, that should go downwards because that's a negative. All right, but the sketch is there just to see where, so you see where the cosine, the angle comes from, the reactive power, sorry, the real power over the apparent power. All right, you can get that angle from the current phases or the voltage phases or the power. Yeah. You could get a question like this in the exam, but I will, after a few weeks, I'll slot in full exam questions on stuff that we've been doing after that day. All right. Yeah. So next bit is I'm gonna go on a new page because this next bit says from the so from ST, the tool S, is equal to IT times E. We can find IT because it is ST over. Yeah. And ST was 1997 angle minus 53 degrees. Yeah. Over 200 angle 0 degrees. sorry, 9 point, yeah, 10 amps. Yeah, we'll go 9.98, 10 amps, angle minus 53 degrees. Alright. I mean, you make a judgment call here. We're looking at improving the power factor from 0.6 to 0.8. He's dropping off hundredths of an amp from out of 10 amps. Going to make a great deal of difference. In this instance, no. So you have to make a judgment call about how much difference that could make later when you drop decimal places. All right. I mean, rule of thumb, I usually work to 3 for a final answer, 3 significant figures. That may mean in calculations earlier that you then go on to use again, you allow 4 significant figures and then round your final answer to 3. But rule of thumb, 3 sig figures, it's not too bad. Alright? And you're a little bit out in the exam, you're not going to, you know, if you've made a mistake, you're going to lose marks. If it's a little bit of a rounded thing, you probably aren't, alright? It depends on how much difference it makes. So, total current flowing under the current power factor is 10 amps. The angle of 53 degrees, in terms of how much current we're going to save through them cables, is not significant, alright? But we keep it there because we might want to use it for calculations later. So the next bit is find the value of capacitance required to reduce the power factor to 0.8 lagger. Right. D. So we've currently got this situation, and I'm going to draw the triangle this way up. Right. We've got the red triangle there. Cos of the angle is currently 0.6, and we've got 1596 var on that line, and we've got 1200 watts on that line, and we're looking to reduce to a Q new, yeah, such that this angle, or the cosine of this angle, becomes 0.8. That's what we're looking to do. Yeah? And therefore, if that's the Q due to the capacitance down the other way, that's making the difference, can you see that that between there and there is the Q supplied by the capacitance? Yeah, it goes down, but if we look at the difference between where Q currently is and where we want it to be, if we find out what Q new is and take it away from Q now, we'll end up with QC. Follow? Yeah. So, what we can say is cosine of the angle is P over S. Right? And therefore, S is equal to P over sine of the angle. Right? That will allow us to find what I'm going to call S new must be power which doesn't change divided by the cosine of the new power factor, 0.8. Let's just write that. Power over angle new. Yeah, that's 1200 over 0.8. What we're now finding is the new apparent power that would give us, that we'd get if we move this power factor or cos by 0.8. Yep. So it equals 1200 over 0.8, 1500 VA. So we now know that this line, this is S new, and it equals 1500 VA. So we've got another triangle down the bottom here now. I'm going to draw it out. P is 1200 as it's always been, and this is Q new. So how can we find Q new? Yeah, Q new is equal to square root of S new squared, take away P squared. Okay, so just going back up to our earlier diagram, we already know the old Q, we know the new Q, so now we can find the reactive power that's got to be provided by the capacitor. QC is equal to Q old minus Q new. 1596 minus 900, 696 var. Now that's how many volt amps reactive this capacitor's got to provide. We want to know how many farads or microfarads of capacitance we've got to put in. What value of capacitance we need to improve to at least 0.8 power factor. Yep. So another way of calculating Q from last week So we know that Q can also be calculated from E over the capacitive reactance. Yeah. And if we can find that, we can use the other formula, the capacitive reactance, to find the value of C. So we can rearrange that to E of a Q. Well, hang on, that's not E. No, you didn't notice my deliberate mate. E squared. One of the three power formula, remember? We said you could also apply them to the reactive power and the apparent power as long as you pick the right three things. So E squared over XC will give you Q, therefore XC is equal to E squared over Q. That is 200 squared, and that's going to be this QC as well. We should qualify that. QC, 200 squared over 696 equals . Yep. I've got 57.5 ohms. Yep. Hopefully I put 50 hertz in this question. Yeah, I did. Right. Also, we know that XC is equal to 1 over 2 times pi times F times C. Therefore, C is equal to 1 over 2 pi F XC. 1 over 2 pi times 50 times 57.5 equals . In microfarads, please. Yep. 55.4 times 10 to the minus 6 farads equals 55.4 So if we add 55.4 microfarads of capacitance onto the end of that circuit, like it's drawn in dotted line, we'll improve the power factor from 0.6 to 0.8. Yeah. Well, let's have, and the last bit, E, was find the new current. We got this triangle here now, where the power is still 1200. And that's 1500 VA. So S is E times I. We'll call it S new. Call it I new. Therefore, the new current in the line is S new over E. 1500 over 200 equals 7.5 amps. I mean, not massively significant in this example question because there's a small load and a low voltage. But when we start, if we converted that to kiloamps, we would have gone from 10 kiloamps to 7.5 kiloamps, losing 2.5 kiloamps. So you can imagine the difference that might make in the main power line cables. They aren't changing size, but it means you can get more real power down that line. You can supply more real power and do more work. Yeah? Well, you don't want to put too much in because that become too costly. Yeah? But you can see that if your reactive load is changing, motors starting up and stopping, like big compressors, they used to have compressors with 100 horse motors, they're starting and stopping, you want to be able to react to that, because that's your power factor is going to be going up and down, and therefore you want to switch capacitance in and out. But you're never going to hold it. It's not infinitely variable. It's done in steps, so to try and keep it within a band. And a 0.8 is something that is 0.8, 0.9 is what's aimed for usually. All right. And if you look at inductive loads like big motors, that'll tell you what their VA rating is. Transformers are rated in VA. That'll tell you what the VA is, and that'll tell you what the cosine, the angle is as well. They're usually about 0.8. Yeah. Yeah. That could be why, yeah. That could be why. Yeah. Yeah. Alright? Are you all happy?